Good morning, ladies and gentlemen, and welcome to the SAIEE Nuclear Chapter webinar on real nuclear costings for South Africa. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to ask a chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Nuclear Chapter playlist. You will find the registration link in the chat box. Please click on it and register. It's free. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our presenter today, Prof. David Nichols, who is also the chairman of the SAIEE Nuclear Chapter. He was appointed as the chairperson of the board of the South African Nuclear Energy Corporation, NECSA, in January 2020. Prior to his retirement at the end of December 2018, he was the Chief Nuclear Officer at Eskom. Internationally, Mr. Nichols was the chairman of the IAEA Technical Working Group on Light Water Reactors from 2010 to 2016, and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operations. He was a member of WANO's post-Fukushima design review team from 2012 to 2018. Over to you, David.
Thank you very much, Minx. I'm just going to see if I can, what have I got here? Get my screen sorted out. Fine, that's it. Can you see that, Minx? All right, up with that.
Perfect. Please proceed.
Okay, thank you. Today's talk is basically going to be trying to put in 1 hour some basics about costing of nuclear power stations, and in a sense, therefore, costing of the power system as a whole, because much is being talked about what the cost of nuclear is, and it's all too expensive and everything else. And people are quoting numbers which don't always make a great deal of sense. So what I want to talk about today is go through this costing issue and hopefully open a debate up. I'll also show a spreadsheet that is available online if you want it to look at some costing issues. But let's go on. Okay, so what I'm going to go through is what are the fundamentals of electrical generation economics, and that really is looking at grid requirements versus the levelized cost of energy, which everyone quotes. What is the levelized cost calculation? How does it work? And then in the nuclear power plant, I want to discuss briefly what the operating costs of a nuclear plant, what the capital costs, the decommissioning costs, the financing costs. So an example of an application of those numbers to what the costs are, a bit of world experience, and then some discussion of the South African option. So quite tidy. I'm going to go reasonably quickly, and I'm hoping that it makes sense. Please, questions at the end. So what are the fundamentals of generation economics? Well, let's just first of all look at, there's a couple of things that I'll put on the table, and I'll start with the obvious one, which is what's the impact of time of use. People talk about levelized cost of energy as being the cost of energy produced by a machine. So if I have a solar panel on my roof, it comes in at maybe between 50 cents and 1 rand a unit from a generation set. And that therefore is compared with the cost of power from, say, a coal station or a natural gas station or something else. And quote, look, it's cheaper. There is, however, a fundamental problem. We actually want power 24/7. And one of the things that is not much discussed by the supporters of renewables is this, what is called the duck curve. And this is actually a real example. This comes from South Australia. That's not South Africa, that's South Australia. And that was Sunday on the 26th October last year. What you can see is that the normal demand that everybody would accept in the standard historical, if there was all grid supply, it would be this top line across here. But in South Australia, there is an enormous amount of solar PV, as is coming in this country now. And so what happens is when the sun is shining, you end up with that being the actual grid demand, because the domestic solar plant is producing this power here. Then you've got a bit of solar here, and you've got your gas turbines sitting down the bottom here as well. So what you're seeing is the fact that when you get to evening peak over here, which in their case is, what are we, something like 7:30, you actually have no solar, and all your classical plant has to work flat out. Whereas at midday, you've got so much solar, both in terms of the domestic solar and the installed solar on the grid, that in fact you are exporting power to the neighboring states. And what's interesting here is you can see quite clearly the imports, that's the gray bit at the bottom, which is coming out here, and overnight you're importing because there's no solar in the day. So this works well to an extent, but what you can really see is that you can't just value the average price of power as a relevant, because if you will all solar, you would have no power here. So that's just an example of what we're talking about in terms of the time of use. And what actually happens midday in many grids is that the price of power on the grid has probably gone negative midday. In other words, people are being paid to take power. And that happens quite regularly. In California, for example, literally about half the days of the year, it goes negative on the grid at midday because some things have to keep running. And what you also can see quite clearly here is people will talk about grids that are connected to other grids and will say, look, the renewables are meeting 80% of their need, but they're only surviving because on some occasions they are exporting power to the neighboring grids, and some they're importing power. And this works, of course, as long as you're the only grid that is running solar plant and none of your neighbors are. The other issue about cost of power is the impact of location, and this is actually more complicated to work out. But this is an example that goes back to 2000, so it's not new at all, but it's an expectation of the value of a 100 megawatt generator in this country at various locations. So they're saying is that if your power station, if you're adding 100 megawatts to the plant at Ellis Ras, which is now Lepalale, you would be looking at it only being worth 98 megawatts to you. Whereas if you're installing it in Cape Town, your 100 megawatts is actually worth some 23 megawatts to you. And what you're seeing here is the cost, both in terms of infrastructure and in terms of line losses, of getting power around long distances. And that's something which is not really modeled very well, and certainly in the IRP wasn't modeled particularly well. When you put all these things together, you can come up with a correction factor to the price of power from different power sources. This happens to be one done in 2018. It's done by the OECD through their NEA, which is the Nuclear Energy Agency, but it's an energy of the International Economic Cooperation Development Organization, which is the major powers in the world. And what's interesting here is they've done 6 different countries have done this study. You had different technologies: gas, coal, nuclear, onshore wind, offshore wind, residential PV, commercial PV, and it said, if you add power to the grid, what does the grid have to do to use that power sensibly? You may look down here at something like gas, very small numbers. And I'll come back to what these numbers mean. Like very small numbers. That's because natural gas, you can classically, they're small machines and they can get put where you need to on the grid. So the grid expansion is not a big issue. The connection to the grid is not expensive. Coal is more expensive primarily because you end up saying, my coal field is not normally near a town, it's out, so you've got some connection things. And as you get to slightly more coal in your system, it goes up. And same with nuclear has got a different problem. Again, it's normally farther away from cities, and also it needs more grid stability. Coburg is seen as the most important load on the ESCOM system. So if the country loses power, Coburg is the first thing to get power to it for safety reasons. So it's more expensive again. So those are classical integration costs, grid integration costs. And then you come across to these other options, onshore and offshore wind and so on. So And what you can see is these are quite high numbers. Now, put it in context, this is a 2018 study, that's 5 years ago, but $40 a megawatt hour is around, what are we, 80 cents a unit. So in other words, if I put, so here's 15, so if I put onshore wind and I've got 10% of my grid fed by onshore wind, I have to add over and above the energy cost for the wind, I have to add in a further $15 a megawatt hour, which works out to about 30 cents a unit, to the entire grid system costs. That's not the cost of the wind you're getting. That means that your overall tariff will be increased by the grid strengthening requirements and so on and so on. In the extreme case of commercial PV, we're looking at something like close to a rand a unit being added, not by the cost of the commercial PV, but by the cost of the grid strengthening. So essentially, if you take residential PV and you say it's sitting at 20, to sake of argument, 40 cents a unit, that's not 40 cents a unit being added to your PV, that's 40 cents to everybody's bid to get 10% of PV on the system. And this may be seen as a bit extreme, and surely this is someone studying it, but the reality is that when South Africa went out in 2020 for 2 parallel requests for proposals for the for both the risk mitigation IPP and the renewable IPP at the same time, one of those bid window 5 versus, the only difference was that one of those said, that's the risk mitigation, said, you must provide me with dispatchable power from 5 in the morning till 9 at night. And the risk and the renewable one said, you must just provide me with solar power when it's available. The difference in the tariff they were bid in at the same time, roughly speaking, in terms of economic conditions, was 4 to 1. It was 4 times more expensive to have power coming in, which was meeting the dispatchable requirements between 5 in the morning and 9 at night, than it was just to have renewable, which gives you an indication of these costs. So that's just to say that you should be careful with LCOE, because LCOE is a calculation which is based upon dispatchable. So what is a levelized cost calculation? You may have all seen this in the press. People will talk about the levelized cost calculation of this technology as X. So let's just talk about it. I took a definition out of somewhere. I'm also not sure I got it, but levelized cost of electricity is a measure of the average net present cost of electricity generation for generator over its lifetime. I put that in English, or my version of English, which is the tariff the plant should charge per kilowatt hour to recover all its costs over its entire life cycle from its electrical output, if that makes sense. So what that really means is that when you start your plant up, you've induced all the costs. Well, let's go to the next slide. So there were 2 balancing accounts in this calculation. So the first is the revenue generated from operation of the plant, and the second is the costs that are incurred in building, operating, and decommissioning the plant. Now, what's important to understand is to get these in balance, there has to be an adjustment to this cost income to reflect when they occur. Clearly, the initial capital will incur interest cost if not immediately matched with income. And the income in year 40 is less valuable than income in year 1. And this is done by adjusting called net discount rate. And this is the degree of discounting the values into the future for a given percentage per year. So if the net discount rate is 10%, then $1 paid in a year's time is only valued at 90 cents today. And $1 in 2 years is valued at 81 cents today. And these are all real interest rates, and I will just be quite important. Nominal is the value in the currency of the year you're talking about. In other words, if I said something's worth a certain number of rand today, if I go back 20 years and I say it's the same number of rand, we would all know that 1,000 rand 20 years ago is worth far more than 1,000 rand is worth today. Now that's just inflation. So the real value is after inflation has been removed. So if we want to quote that, so everything we're talking about here is in terms of real, and the assumption, for example, if you generate a tariff, is that tariff will be indexed to inflation. It also means you can talk about interest rates, that if somebody's charging you 10% interest rate, but inflation is 5%, then in reality, you're only getting 5% interest, which is half the amount. Okay, let's look at a calculation and see if I can make some sums of English here. So application number 1. This is not a technology power station. I've just used some numbers here, so please don't run off and think this is the cost of any particular power station. But I've got this power station which cost me $100 and produces 1 kilowatt hour per year. So it's a pretty ineffective power station. It runs for 20 years. It has no operating costs, but it costs $15 to be decommissioned at 20 years old. So what's the levelized cost if the net discount is 10%? Well, the first year's production, so I'm now valuing it, is valued at 1 rand, 1 kilowatt hour. That's the value of the first one. The second year's production is valued at 90 cents. The third year's production is valued at 81 cents. And in fact, the 20th year's production is only valued at 13.5 kilowatt hours, kilowatt hours. So the overall value of the production is, add all those up, and you can do it in spreadsheet one, I didn't, but is 8.8 kilowatt hours. So I built this station, cost me $100, and it's going to make 8.8 kilowatt hours by my valuation. The decommissioning cost of $15 in year 20 has a current valuation of £15.135, which is that ratio, and it therefore comes to $2.25. So there we have it. So the levelized cost of energy from this plant is $100, the cost of buying it. The present value of decommissioning, which is now $2.25. And we've produced, in today's valuations, 8.8 kilowatt hours worth of energy. So the levelized cost is $11.61 a kilowatt hour. And as I said, these numbers are just numbers. Please don't read anything into it. If someone came with a business case of $11, you wouldn't get very far, but okay. So that's all very good, you say, that's fine. Let's just look at what happens if I change the discount rate to 10%, to 3% rather. Now, what happens now is that the production values here get worth more because you're discounting them less. And therefore your value of your production has gone up from what was 8.8 to 15.2. Your decommissioning cost has also gone up because you're discounting it less. So it's gone from $2 to $8. And therefore your levelized cost of energy from this weird plant has gone to $7.58, or only 65% of the 10% discount rate value. This is an important understanding. In other words, I have not changed the cost of building, operating, decommissioning the power station. I've just changed the discount rate I'm assuming. And we'll come to discount rates a bit later in this talk, or what discount rates are reasonable. But I'll put a thought to you very quickly in our head is that if you are claiming a discount rate of 3% in South Africa today, with inflation at 7%, that means your actual nominal interest rate is 7% plus 3% is 10%. So this one is saying you're getting 10% nominal interest rate. This one here would be saying you're getting 17% nominal interest rate. So it's quite an important number. You can see the impact it has on the overall discount, the overall discounted LCOE. Okay. Why is this any importance? Well, let's give you an example which is very real and very current. I'll bring up this cost curve a bit later, but this is a curve which says, given that I have got a certain capital cost for my power station, and we measure capital costs in dollars per kilowatt installed, and you can see this, the bottom curve is at 2.5. This bottom curve, the blue curve, is at $2,500 a kilowatt. There, which of interest is the kind of price we're looking at with the domestic programs in South Korea, Russia, China, India, and so on. At the top end, this red one here is looking at $6,000 a kilowatt, which is probably the sensible upper end of the cost of building a new imported plant. So that's the learning. What you can see is if I use this bottom bit is discount rate across here, and if you use 8.2 or 8.3, which is the number used in the IRP, then you end up with the $6,000 a kilowatt person costing you something like 1,800 rand a megawatt hour, or in the order of 1 rand 80 a kilowatt hour. But if you take if you then use export credit agency financing, which we'll discuss a bit later, then exactly the same curve with the same input numbers gives you a figure of below below a rand a unit. So clearly you can choose a discount rate, which is not an interest rate. It is an assumed your view of value for future money, and you will end up seeing that change being that drastic. But so that's the bit of LCOE. I hope it made some sense to you. Let's talk about the costs that go into making up the input. Well, the first one's operating costs, and these are very simple. Nuclear fuel is well understood. It's about $5 a megawatt hour. And this aligns with Eskom's quoted Coburg primary energy cost of about 100 rand a megawatt hour, about 20 to 1 nowadays. Eskom actually does include some various ancillary costs, e.g. water, and spent fuel disposal in this cost. So that's a $5 a megawatt hour. You'll see I'm looking in dollar terms because that's how the industry operates in terms of costings. I'll show a bit later some results of this, but the NEA OEC report, which is 2015 edition, projected cost of had operating and maintenance between $27 a megawatt hour, which was Japan, down to $6.50 a megawatt hour, which is China, with an average of $13 a megawatt hour. Only 2 of these, of the 11 values, being above $15 a megawatt hour. So you'll see that I'm just adding the 15 to the 5, and I get 20 as my reference cost. Overheads is a corporate overhead difficult to assign, so that depends on the principles, and you must be careful when you put those in there. You may end up with some weird numbers. I will comment that operating includes decommissioning provision. That's included in our company decommissioning in a second. So totally, for the purpose of these discussions, I use a figure of $20 a megawatt hour for overall operating costs. Eskom's running Coburg, their coding figures, 45 cents a kilowatt hour, which is somewhat over the $20, but it is reasonable given that all of Eskom's nuclear fleet overheads are included in 2 units. So in other words, South Africa today has 2 reactors, and everything we do to do with the fleet costs, that's licensing, management, all those things are carried on those 2 units. So we have quite a high overhead on our nuclear program, which would not increase if we built more machines. There's no logic to building machines. So that's how we get to $20 a megawatt hour. Just of interest, this is the actual extract from the Eskom holdings, March 2020, and you can see Cuba nuclear sitting at 100. And this is primary energy costs. Again, people could quote this as being the cost of nuclear. It's not. This is the primary energy cost. It's the cost of buying nuclear fuel, spent fuel disposal, and other bits and pieces, which is why some of these figures are quite high, because they're total. So the IPPs is the total included cost, as the right, capital costs. Okay, that's operating cost, about $20 a megawatt hour. Everyone says nuclear is horribly expensive, and they quote the disasters in this world. And I'll just quote an article again, 2019. It's from Financial Times, and this is a quote, direct quote from the article. It said, analysis of Energy Technology Institute, an organization backed by the government, and looked at 34 delivered nuclear projects around the world. And they said there was a chunk of them which we call first of a class in the USA and Europe, and they come in at $9,000 to $12,000 a kilowatt, or even higher. They are really disastrous projects. But only 15% of the overall ones came in over $5,500 a kilowatt. 45% were between 5.5 and 3.5, and 40% were below 3.5. And I will say now the 40% is basically the serious production in countries as domestic programs. So that's the domestic program in China, in Russia, South Korea, India, and so on. It's very interesting to note that the standards applied to nuclear build are common across the world. So there was a bit of comment historically when Eskom was getting its new steam generators for Coburg, that these were coming from China. Do we trust the Chinese? The answer is yes, they have the same standards. They're exporting from the same plants. So the nuclear industry is very, like the aviation industry, it has very common standards across the world. Of interest, what are the current, so that's just an article that someone wrote. I just dug out the current costs, and there's approximately, this is public statements. Now, this is the cost of a series of projects. You can see export projects. I didn't look at domestic projects. And the cost is rounded up in this. The actual calculation was done with a more detailed cost. And the scope includes various things. So each of these projects some of them include fuel and O&M. For example, the Bangladesh includes the Russians operating the reactor for the first year in toto. We know that the UAE one includes the owner's cost in that number, but also includes fuel for the first 6 years. Most of these include fuel for the first about 6 years operation. And what you can see again, and these are fixed price export contracts. This is Chinese. So the HPRs, the HPR is the Chinese machines. That's two Pakistan contracts. The first contract was 2 units. The second contract was placed a few months ago and is for 1 unit. You can see the value. If you go from the Pakistan at 4734 to 3283 of building follow-on machines, your learning is dramatic and your overheads get reduced. India, VVRs are Russian. And what you can see here is the costing breakdown fits well with the discussion we had previously. I will note that all the domestic projects in China, South Korea, and Russia are quoted as below $3,000 a kilowatt. What is interesting is, again, you can see the one outlier at the bottom here. The bottom 3, which you can talk about slightly, or the bottom 4. The UK one is the French building an EPR, and that is showing the impact of very slow construction, and European approach to overkill. The Egyptian's interesting because it includes 2 very large desalination plants in the project, and its total cost, including operations and maintenance, first 10 years, support for the first 10 years, but it includes 2 big desalination plants to provide enough water to supply the entire Alexandria, and includes a sort of 160-kilometer pipeline and everything else. Hungary has specified that the Russians changed their design to meet what they call Western standards without defining them. And Bangladesh is interesting because it's the one where the Russians actually even funded under what is loan, they funded the development work. So that's a whole. So that's the kind of cost of the real world today. So we'd say somewhere between 4,000 to 5,000 seems a reasonable number for the average one. I could go on for length of that. So that's the little price we're looking at. And this just of interest is construction times. And I'll mention it because time is a big driver of cost in these projects. This is this red blocks here is well-run programs. So you can see there's the French program initially, the blue stars there, and you can see the last few when the was slowing down, it got worse and worse. This is the American one, which started off pretty well and then just recently. And then you can see that the South Koreans are down here and the Chinese are down here. So again, you've got a figure that says, yes, you can make mistakes, but essentially the present state of art is about 5 years construction. Just put it a different way, I just plotted a couple of years ago, and I apologize, I think Flamin and Olkiluoto are worse than this now. This is the concrete to commercial completion date, commercial operation date. And you can see that the average is 60 months. And there are ones that stick out. So here's Kalinin 3. And that was because it was the construction was shut down during after the collapse of the USSR and was then restarted later, so it isn't me. There's the 4 in the middle here, shoes B1, B2, and Shiva 1 and 2 were French ones that were built and really where the whole design was a problem. The red ones are Coburg 1 and 2, and they're interesting because we had sabotage, so essentially you could argue very strongly we had 18 months at least added to that project by the sabotage on site. But essentially, what can be seen here is that it's quite conventional to sit here. And over here, we've got Olkiluoto and Flamanville, which I won't even discuss much because they're the ones that are currently in disaster. So there's the things. Here's Daya Bay, which is the first Chinese rent. So you can see his first machines take longer, but something like 60 months, 50 to 60 months is a reasonable time for construction. And that goes back to the previous cost numbers. The other one that's just going to mention, I'll mention it very quickly in passing, is as you build more plants, your cost goes down. And this is just 2 interesting graphs. One is the localization by equipment in China. That's Guangdong, Lingao, and I'm not even going to Ningji. What you can see is the Chinese achieved an increase, each of these is a unit, But what you can see is as they went on, they got more and more locally. And by the time they got to unit number 6, they were at 70% local content for the components in the plant. Clearly, the concrete and civil works were 100%. So it can be achieved. This of interest is the Koreans. They built a standardized design. This wasn't their first reactor. They'd built some reactors before this. They built a standardized design, and so that's the kind of cost savings you get over building a series. It's learning. It's not included in the IRP calculations because IRP calculations didn't include learning in this sense for a nuclear program. Okay, decommissioning costs, very sensitive. Everyone gets on decommissioning. This is the NRC statement. I just pulled this out, but it's because essentially it's in the order of 10 to 15% of the actual initial construction cost in real terms. Now, Coburg uses, I think, Coburg's numbers worked out in detail, becomes about 15% of the replacement cost of Coburg. This is the US statement of the NRC, $300 to $400 million, which is less than 10% of the construction cost of a standardized plant at $5 billion. So the Americans have decommissioned a number of reactors in this field. So this is a safe number. And you may say, but that's 10% on the cost of the plant. But if you remember the decommissioning, the discount rate discussion earlier, if I've got a 60-year life and I've got 15% of the capex put aside as decommissioning money, if I have no discount rate, and clearly I'm 15% because there's no discounting, but if I discount up even at about 3% discount rate, I end up with about 2% of the cost of the plant being a factor of decommissioning. So decommissioning is not a major issue if it's the only problem with decommissioning is if money is not put aside over the life of the plant. When you get to the end of the plant and the plant is no longer making revenue, and therefore it becomes a liability to somebody, and that's an issue which is clearly relevant. But in terms of the economics, it's not really an issue if you're up, down, and certainly if you're at something like 8%, which is the number used in the IRP, decommissioning is irrelevant. Financing, I mentioned discount rates a lot. So just quick comment, everybody, like buying a motor car when you buy a nuclear power station, all vendors offer export agency, credit agency financing. I quote that not much of it is quoted publicly. We know the numbers because it was quoted for Coburg, but South Africa when we were going to build nuclear 1, and it was quoted at about 2% real. This is interesting because it's just an Egyptian statement, $25 billion being financing the building of the nuclear power plant. So the whole thing is being financed by the Russians. And they're quoting 3% annually according to the Gazette. Essentially, this standard approach of export credit agency finance for a large project is that you get loaned the money on 85% of the project cost. You get loaned the money normally at a highly competitive rate, which is 3 or 4% nominal, which is actually about 2% real. And you start repayment once the machine has started up and is productive, and you have 18 years to repay it, which is what they're sort of saying here. And by the way, Egypt's credit rating is lower than South Africa's credit rating, so Bangladesh is also not too kosher. This is of interest, so you say, well, does that apply to ESCOM? ESCOM does have export credit agency financing. This is extracted again for the annual report in 2018. And what's interesting is those are the interest rates. So these are not for nuclear projects, these are for non-nuclear projects. So you can see the interest 1.58, 0.78, 0.62, 4.73, 2.5, 9.6, that's in South African rands, 2.3. You take off the inflation rates in Europe and the States of about 2%, you end up with figures that in some cases close to or less than zero. Important to understand that is what the real financing is as you see it going forward. Application, I mentioned that graph before. So this is all that background information put into a curve. And I haven't said what the cost of the plant is, but I've said that we quote it at the cost between, I've gone, this graph goes between 2,500 and 6,000. 2,500 is the bottom end of the range. That's what the Russians, Chinese, Koreans, and Indians are building as domestic projects. $6,000 should be the upper limit of any credible export deal unless you are trying to do something rather unusual. What can be seen is that at 3% discount rates, we're looking at figures even for $6,000 a kilowatt of about 90 cents a unit. What you also can see is if I change from 3% to 8%, I go from 90 cents a unit, which makes it highly competitive, to £1.75, which in the IRP sense makes it just off the scale as uncompetitive. So what you suddenly realize, your discount rate is almost more important to you than your the cost of capital is almost more important to you than the cost of the plant. But certainly figures of in the order of 5,000, which is this orange line here, is probably a reasonable number to use. If we're in negotiations, you'd hope to get less, but you might not. And that would include the owner's costs. Owner's costs being the cost that is not part of the plant built by the vendor. So it's things like transmission lines, buying the land, training the operators, and so on. Put it a different way, again, the OECD does a report every 5 years. I haven't done it 2015, there's a nice graph in there, but it's the same thing in the later one. Nuclear Energy Agency does it. What they do is they go out and they ask everybody, literally, they ask every country in the world, can you please tell us what your costs are for plant, operating, maintenance, capital cost, the whole thing. What do you think you're going to build? And everyone comes in and gives them their numbers, and using a standardized LCOE calculation, they crunch it, they put the numbers out. And they do it, in 2015, they did 3 discount rates, 3%, which you say is a state, they see as being a state regulated business, up to 10%, which is an IPP. And then for all so I think the blue blocks, which are the nuclear ones, for each of the sets of data provided by countries, they work out what's the lowest price, it's probably Chinese one, and what's the highest price, and what is the median, right? I think that's the median figure. What you can see is at 3% discount rate, combined cycle gas turbines are more expensive than coal, which is more expensive than nuclear. And in fact, there is almost no overlap between coal and nuclear. That's because most of nuclear is capital, but operating is really cheap, whereas with combined cycle gas turbine, most of it is operating cost, i.e. buying natural gas, and the capital is really cheap. So what you can see is as you increase the discount rate, which increases the cost of gas, which increases the essential cost of interest on the capital, the combined cycle gas turbines hardly change. The nuclear gets worse and worse. Coal is somewhere in the middle. And these are lovely examples. So what you can see is if somebody says to me, I'm the state doing it at 3%, then suddenly you say from this graph, it would seem, and I use the data name, internationally everyone's accepting that nuclear is the most cost-effective way of doing it. If you say, I'm doing it 10%, then it probably becomes a toss-up. The median sits with, the median cheapest is coal, next natural gas, next nuclear. So clearly this cost of the expected discount rate of what is the value of future money becomes a massive issue. And essentially what you can say is something like 3% is if the state is doing it. And as you add risk by being a private sector, you go up this line. So quite simply, because 3% implies a long-term view, it implies stability in the system, and the state controls that. If you're dealing with the private sector, then you're at risk of market variations, and that sits out at 10%. So this means that depending on what number you use, with exactly the same input data, I can either say nuclear is the most expensive median option, which is over here, or the cheapest. And both are true. But you've got to look at what discount rate actually is. And I want to go back to it, what ESCOM actually got for its discount rate. Look at some real world experience. Just of interest, this is the 2015 data from British Petroleum, who put out stats every few years and it's just looked at the tariffs in different countries across Europe, and it plotted them against the amount of installed solar capacity and wind capacity. And what you can see is a nice correlation, which says that if you are lots of wind and capital, then you are somewhat expensive, and if you're down here with old-fashioned technology, you're a bit cheaper. The other one is to say that we're going to is, and it's really almost a side issue from the cost, but it's relevant because the argument for renewables is it brings my carbon intensity down. And what you've got here is, again, a European graph. Each dot is 1 hour over the year. So each of these is 8,760 dots, and each color is a country. So here is France. So managed generation in kilowatt hours was quite a lot in each hour. And what you can see is France is nice and low down here. That's nuclear. You can see Norway that's Norway. That's Sweden, SE. That is Switzerland. I know lots of Switzerland, and so on. So what you can see down here is the countries. That's a nuclear country. Switzerland's actually half nuclear, but I don't really realize it. The rest is hydro. Norway is almost entirely hydro, and Sweden is about a third, 1/3 hydro, 1/3 nuclear, and 1/3 other things. And then you can see the rest of them. There's Poland, an algorithm for South Africa, very heavily coal-based. What is interesting is that this line here is that color there. You can see that purpley color, that lavender color. That is Denmark. So Denmark was not. And this is on the left-hand side. It's a small country, but essentially you can see that it's getting quite high at times. Belgium's down here. That's half nuclear, by the way. Spain, a lot solar. This is Germany. This is the supposed one that has got the answer right, and you can see there the CO2. So moving on just a bit further, this is also an interesting graph. This is just again, I pulled this off from Statistica 2023, which just says household prices. And again, I believe if you're going to talk about things like energy solutions, you've got to look at the fix. So what's interesting is there, South Africa, we're down or whatever this looks, that'll be 15 cents, which is about £2.50, which is where we are. This is the Denmark, Germany, United Kingdom, Italy, Spain, Ireland, Japan, Rwanda, Australia, and so on, which shows you these countries here. I didn't select this. This is the graph they provided, or the data they provided. What's interesting is those countries are all building nuclear power plants. As is, by the way, the French are doing it and the UK is doing it, but I said earlier they're somewhat expensive. But that's the guys building nuclear plants in the. So it's interesting question of who's doing it and why. Last question before I get on to calculations for is people say, well, I can go off grid, and this is a study done, in fact, for Tanzania, but it doesn't make a difference where in the world it is because your component costs are similar. And this is the results of heavy residential and business load profile. So if you want to go off grid, and this is off grid, not grid tied, because grid tied, it means you're using ESCOM at that evening peak and the morning peak and just taking advantage of the middle, is they worked out, this is a bit of guess, so the exchange rate's changed, it's worse than this now. But if you go for diesel only, it's 90 cents US, PV plus battery, 96 cents, combination, 11 rand 90 a kilowatt hour. And business heavy is 9 rand 52 a kilowatt hour. So what you can see is going off grid. You want to go off grid, off grid, off grid, then the study by USA, Enwell, which is a US national lab which works heavily in renewable area, Power Africa, and they're saying is that no, this does not compete with any of the solutions that are grid linked. Okay, what are our options? I'm now going to try and be clever and concerned at times slightly, but I've nearly finished. This is a calculation that I did, and you can see this. I'll show you the website where this comes from a bit later. At the end of the talk, 3 slides to go. And this just says what happens in South Africa. Okay, let's start off with, we're going to have a $5,000 a kilowatt electric power plant. And we say the owner's cost is 15% of that cost. So in other words, we're going to spend $5,000 a kilowatt for the vendor to buy the machine. But if at our cost of buying the land, sorting the infrastructure out, training the staff, and there's about 15% of that, which is not a bad number. Should be a bit lower than that, but it's not a bad number to use. And I'm saying 60 months from first concrete to power, which goes back to that curve we saw earlier. I've then put in, we've got ECA terms for 85% of the project costs, which is what the standard number is. I've got 18 years to repay it, and I'm being charged interest at 4%, which is higher than that Egyptian quote I gave you earlier, and higher than most of the ones that Eskom's got for its current ECA financing. We put 2% inflation in the country. So this is in dollars. Then we're saying it's 2% they've got 2% inflation. Current inflation is much higher than that, but I'm looking at the last 10 years. We're saying it's going to last for 60 years. It's going to have a load factor of 90%, which is standard, and it's going to O&M a fuel $20 a megawatt hour. Decommissioning costs 15% of the EPC contract mentioned earlier, and 10 years of activity post shutdown. In other words, you don't spend it all the day you shut down. You spend it over the next 10 years to shut down. So what Koeberg's plan. Discount rate I've used for the equity finance is the same one that is used in the IRP, but for the local non-ECA debt, in other words, South African interest rate, I've assumed 11% interest rate on the debt you raise and a 5% inflation in this country, $18 around the dollar. Then comes the interesting thing. What this little model, and it's just an example of where there's many ways you can skin this cat. We've said that for the first 10 years of each plant, you give it a R1.50 PPA. In other words, you would end up with the machines being paid for the first 10 years of their life, a bit about the bottom of the range of the risk mitigation IPP bids, but only for 10 years. And then once that's over, you get paid 90 cents a unit, and Koeberg gets 90 cents a unit. I've assumed that we're going to build 4 machines. First machine, ordinary the model is 2032, so just understand that. I've assumed they're 1,400 megawatt, which is in fact Korean APRs. I've assumed 1 year between the machines and 4 machines in toto. I've assumed Koeberg's power is 1,065, which is what it should be with the new steam generators and the thermal uprates. And I've assumed availability 85% of Koeberg. It's an older machine, older technology slightly, so it shouldn't be quite as good as them. And costs of Koeberg at 40 cents, which gives you an income of about net income. In other words, cash free from the Koeberg operation, about 8 billion rand a year. So if Koeberg was a PPA today and was running properly, a couple of years from now when the upgrades all been done, it should be generating a cash flow of about 8 billion rand a year after all costs are paid. I've also assumed that we're going to fund some small modular reactor project for parallel to the large reactors at Pelindaba, but a billion rand a year for 8 years. And then I've also assumed this model takes over the Eskom debt it incurred for decommissioning, not for decommissioning Koeberg, for the life extension, which they've mentioned 20 billion rand. We've also assumed Koeberg's decommissioning's in here. So what that tell you? It tells you if we did that model, so if we ring fence Koeberg from 2024, and we said we are going to give Koeberg a debt of 20 billion rand to start with, we're going to force it to pay some money towards a small modular reactor program to be on the high felt. We're going to give it a PPA at 90 cents, which would be very good today. In other words, the grid should like that. That's the market rate for Koeberg, and the new machines get the IPP rate. Then this will be cash positive the whole way through. Now we're talking about 4 times 1,400 megawatts. What's that? That's get it right in my head. 5,600 megawatts, and we have a peak ECA debt of 439 million rand. The levelized cost of energy from this, with the ECA financing included, but at the discount rate of 8.2%, is R1.17 a kilowatt hour, with no ECA. In other words, just as it's assumed in the IRP model, R1.59. So that is basically the kind of numbers you come up with. That would be, I think, a very good deal for the country. I'm trying to put the numbers here all well based. You can easily make the numbers more favorable if you try. But people will say, well, excuse me, but there's no way this can really happen in the time frame to help us as a country. And to some extent, they're right, because it'll take 10 years to get the first machine online. I'm saying if we're really aggressive, we could get the first machine possibly 2032, and then 1 year after that. So clearly, nuclear is just too slow. That's the comment everybody makes. Well, just a quick second. This is the exact data from the French build program. They started in 71, and the purple lines are the number of megawatts where construction started, and the mauve or lilac is where they come online. And what you can see is in 71, they started building their first station, and that came on stream in 77. And you can see that, and they stopped it. So that was the real example. Start from grassroots 71, and by 88, they had 48,000 megawatts of installed nuclear plant running in France. If you redate that and you put 2025 here, you get 2030, 2031, 32, we start seeing the first machines coming online. By 2035, we're sitting at 20,000 megawatts, and by 2040, so it certainly seems to be credible. But is this purely a French example of doing it? And my answer will be, well, this actually is an example again. This was from a science journal. The individual data actually comes from the BP data set, which is one of the world's best data sets. And what this says is, it's a subset, but it just looks at the solar, wind, and nuclear. And it says how many kilowatt hours per capita are added annually in a 10-year period. There's Sweden, 76 to 86, France, 79, 89, Belgium, 77, 87, so on and so on. The best wind is Denmark. And so everyone says, oh, look at the way that we're rolling renewables out in terms of energy production. We aren't coming close to the figures that were achieved by the nuclear world in the 1970s and 80s, when nuclear was the big build programs. So with that, I'm going to come to the end of my spiel. I've that of interest. If you go to nuclearchapter.org.za, you'll find the website of the nuclear chapter, the SAIEE. And if you go to LCOE, you'll find that version of that spreadsheet I showed earlier. So with that, I'm going to hand back to Minx to drive the process. I haven't seen any questions, Minx. I haven't been looking for them. Has anybody got any questions for that rather long?
No problem. Yes, thank you, David. I appreciate that. It was a very informative and thought-provoking presentation. I would encourage our attendees to ask questions, please. I have so far one from Vela Majadu asking, what happens if you exclude Coburg in the model? Is the project still competitive for the SA economy?
Well, yes. I mean, including Coburg in the model makes it cash positive the whole way through. And in fact, you actually can include, with a bit of fiddling, you can include all of our costs of running Nexa and the cost of replacing Coburg's, Nexa's multipurpose reactors, Safari. But clearly you would go cash negative to begin with if there's no Coburg in there. So you could still do it. You would have to raise loans. And I think people often say, oh, but we can't indebt the country. But the reality is all the power purchase agreements are being covered by sovereign guarantees. So in that one, all I assumed was we were getting the 85% export credit finance from the vendor. But in reality, you can get 100% financing. I mean, I said about the Bangladesh, in fact, got their developmental money lent to them by the Russians. There was no money put into their project by Bangladesh. They own the plant at the end. But the same thing's happening at the moment, as I understand it, with the third HPR 1000 being built in China, built in Pakistan, which, by the way, is financially completely bankrupt. And the Chinese are financing that, I think, again, to the 100% mark. So it would be not as good, but it would just have a cash problem up front, as any project does, and requires some kind of guarantees and loans.
Thank you, David. We have another question here from Selimpele. Why was this case
Yep.
not made for nuclear when Eskom embarked on the coal build program in 2008?
I'm not sure I can answer that question particularly well. It was an assumption at that point that nuclear was too expensive. Don't ask the question. And that's one thing I'd say is universal in this whole area. If you look carefully at what happens is the court case in 2017 stopped Eskom even getting the response to the request for information being read. The assumption was and at that point, the then Minister of Finance, Minister Nene, said, we know we couldn't afford a nuclear program. And when asked, did he know what the cost was going to be? He said, no, but I know it's too much. So I think one of the reasons I'm giving this talk today, one of the I'd like to sort of is because people are making a presumption that nuclear is unaffordable and nuclear is expensive and nuclear is not. And the answer is that's not been shown anywhere particularly. There'll be bad nuclear projects, no question. And the problem we probably have is that if you look at what I call the West's nuclear projects, and for that I mean the US one, Vogel, before that summer, the UK one, the French ones, the Finnish ones, all the ones that are being driven by, I'll call it the historical Western vendors, actually going very badly. Alternating it with cost per kilowatt installed up in the order of $10,000, $12,000 a kilowatt because they're being delayed and wisdom. Whereas the people who are building standardized machines, it's not because they're Russian or because they're Chinese or because they're South Korean. It's because if you do something repetitive, you get a lot better at it. Your first one is always a stuff up. And the answer is that the world is restarting its nuclear business. So everyone looks at the French and the Americans and the British and say, look at those costs, they are not affordable. And they aren't looking at who actually is the export drivers in the world. At the moment in the world, in terms of exports and building, there are really two and a half players in the game. There's Russia that is the export dominator. It's got like 80% of the world's export market. It's building a few machines at home because our own economy is not in particular shape, but it's basically got the export market sorted out. And then you've got the Chinese, whose domestic home market is going really well, and is doing some export work, all in Pakistan at this point. The half I mentioned is South Korea because they are very successful at building domestically. They built Bracca in UAE very successfully. There was a problem in the operational side of that and the setup in the UAE, but they had almost an interregnum a few years ago when the last premier president head of the government came in and said we're going to stop the nuclear program, and that put a stop to all the nuclear program in South Korea. And they've just restarted. The new president, just elected, has said no, we're going to build nuclear, go back to nuclear. So they're a player clearly. But if you want somebody who's got a track record of building on time and on budget in the last 20 years, you talk to the South Koreans, to the Chinese, to the Russians. You don't talk to so much the Americans and the French as examples. But yeah, so the answer was in 2004, nuclear was always that funny thing in Cape Town, and coal was the real answer when Medupi and Kusile were committed to.
Thank you, David. We've got another question here from Walter Moilwa. Has a site been selected in South Africa, and how far is the process, if so? What are the challenges, if there are any?
Oh, God, lots of challenges. In terms of sites, Eskom has always looked at the coast for new nuclear power stations. So there are two projects. I haven't mentioned small modular reactors here because their economics are much more, what's the word for it, uncertain stage. Eskom ended up in the late 80s, early 90s, selecting 5 sites, of which 2 essentially are still in the game. One of those is extending the Coburg site itself physically, and the second one is a site called Tastepunt, which is near Jeffreys Bay, In both those sites, Eskom has done an enormous amount of work over the last 20 years, 30 years. So they're both really pretty much ready for starting work on those sites. And in fact, what was interesting is the last few days, Eskom started the EIA for the new build of nuclear in 2006. This shows you the problem we've got in the industry. That's been going through the system with support over the last, 2006 puts into 17 years. And in 2000, and finally in about 2000 and must be 15, 16, there was an EIA record decision finally, after all the appeals and everything else, was a record decision for the site to be at Coburg, or up to 4,000 megawatts. That was then appealed, and the appeal has sat on the minister's desk till now. Something like 6, 7 years on the desk. And only now is Eskom actually going, and now I think the minister's asked for a review of some of the studies done previously as part of her final agreement thing. So yes, we're in the sense of siting, for those sites, we're pretty much, the work has been largely done. I'm not saying it's perfect, but there's certainly, the contracting will take longer than getting the sites ready. The other sites that I think on a small modular reactor basis, we've certainly, and I'll speak from the Nexa point of view, we've certainly put forward the proposal publicly that we think that in parallel with building large reactors on the coast, there should be a project to put small modular reactors onto the existing coal stations as they decommission. There was talk of a just energy transition, and my view is, our view at Nexa is that by far the best solution is to replace the Kamatis, Canberras, Goodflays, Endrinas, and so on those sites with power generating machines of a similar size than the ones they're losing. So our view is we should be rolling out a small modular reactor program on those sites. No serious work's been done, but those sites are, from an environmental, pretty much we think in a good shape because they're brownfield sites. The other site we'd like to put the lead machine of a small modular reactor is on the Pelindaba site, where Nexa is, and that again is an existing nuclear site. So I don't think siting is not an issue, but the political will is the issue always. And the fact that the problem with nuclear power is extremely simple. Despite all the rumors to the contrary, there is no particular way to extract rent from a nuclear program. The financing, the contract is a one contract to a big state-to-state contract. The subcontracts are all done by that big contractor against his fixed price contract, so they're very hard on costs. And the financing is all done through state organized bank activities. So the problem is that if I am a project developer and I make money from making a few percent of each of the deals I get involved with, there is nowhere for me to get into this deal. That may be one of the problems that nuclear has. It doesn't fit into the current economics view of some people in this country.
Thank you, David. We've got a next question from Hannes Lyon. If SMRs were to be proven financially feasible, what legislative reform would be required to be able to implement?
Okay, I can answer your question in two ways. Inside South Africa, if you assume that someone like Eskom or a state organ is running them, the present legislation is fine. There is only one problem with small modular reactors, pardon me, it's just, and that is that if you go into Africa, north of us in Africa, into small grids where you're looking at a few hundred megawatts of new power, then you have a significant challenge because the classical licensing approach is each country has its own unique licensing system and must fully license the plant from first principles. So the engineering overhead of putting nuclear is quite large. It's tolerable with a couple of thousand megawatts of large light water reactors. In South Africa, it would be tolerable, we would have those systems. But if I was going to build a nuclear plant, for example, in the Congo, I would have a problem with having overheads of several hundred people and development costs in a high-tech team that's trying to license the plant. So there's a bit of that But in South Africa, there's no particular legal issue that would stop it. SMRs. The only issue might be the nuclear energy policy as currently written says Eskom is to be the owner operator of new nuclear power stations. That's a policy, not legislation, and I don't think is any more major barrier.
Thank you, David. We've got another question from David Rodda. He's saying, lovely educational presentation, thank you. Question, why would a foreign government fund a nuclear plant for the low rate of 2% real when they could buy a risk-free government bond at CPI plus 5%?
The answer to that question is because you're getting industry, because the reason you do export credit agency financing is to keep your own industries going. So you export credit agency what you are doing in your country. So it is the current practice. It is what governments have done. I will quote you that literally the Chinese just did it a month or so ago with the Pakistanis. So it is the classical way you support your domestic industry. So they wouldn't provide so much export credits for domestically designed and built reactors. We certainly wouldn't get that. But if we are importing a reactor from China or Russia or South Korea or wherever, it is industrial practice to provide export credits. I'll give you a simple example. The biggest user in the US of export credit agency financing is Boeing. Every Boeing aircraft that's sold is sold with a loan package from the US, backed by the US government, and it keeps Boeing in business. So it is the practice, but I think that what is interesting is that the difference between the state doing it and a private sector doing it. Because if somebody says, I'm going to do something at 3% real, then the private sector will say, I want unbelievable guarantees to make it virtually a state bond. If that makes any sense.
Thank you. And Mr. Rodda asked another question. Should we not be adding 50% on the EPC costs due to average cost overruns on large projects? Some say that the UAE Barak cost overrun has sent the price up from $20 billion to $30 billion.
All the projects I listed, except for the UK one, by the way, are fixed price contracts.
Interesting.
When Eskom negotiated the deal, when we negotiated the deal in 2006, and I was on the negotiating team, 2006, 2009, or 2008 for a nuclear deal, the price was, we ended up with about 40 different indices in the price. Let me just explain to you. What we said was, do not give us a single price. We want you to say, this portion of the cost is in copper, for example. So we will have that portion index linked to the LME, London Metal Exchange copper price. We will have this is being made in Japan. So we'll link that one to the yen and to the CPI or the PPI in Japan. So yes, you may get some variation in cost due to nominal versus due to changing cost of raw materials, but you don't. None of these deals at the moment that are except for the domestic deals, none of these deals are being done as cost plus deals. That is not how you do it. And what's interesting is one of the reasons that Areva, as it was, went bankrupt was because they signed the contract with the Finns for Olkiluoto 3, and that plant was a fixed price contract, I think 3 billion euros. It has overrun unbelievably, and the result has been that they've essentially they were taken over. Areva was shut down by the French government and taken over and changed. Was rescued by the French government, and it was interesting that there were two parallel lawsuits going on. One is by the French trying to recover their extra costs from the Finns, and one from the Finns for late delivery. But the answer to the question is you go to somebody who builds it regularly. And if you do a first of a class yourself, it'll cost overrun, no question. But if you go out and you contract and you're in, and all the other deals at the moment are coming in essentially within their contracts as far as we're aware. The interesting, you mentioned BRCA. BRCA was delayed, was on schedule and on budget with the Korean construction, but the problem with BRCA was interesting. BRCA was the first export job of the Koreans. It went as an export job, it went very well from the physical construction, and we know it very well because 140 guys went from Cuba, were recruited out of Cuba to go and help put it together. But the problem they hit was that they had not thought about the organizational quality systems you need as a utility to run a nuclear plant. So what they did was they had the physical plants built on schedule and on budget, but they then sat there and said, we haven't got a license to operate it because we haven't got the expertise, and everything's been done with consultants. So they had to build essentially their own version of ESCOM to do that, which is one reason why any discussion of a large reactor program in this country, in my view, has to be linked to the current Coburg site. In other words, the staff and the skills expertise comes from there. But essentially, these contracts out there now, the ones you're looking at that I quoted are not cost plus contracts. They are fixed contracts, and they've got delay penalty. The delay penalty on the nuclear one was, I think, about $2.5 million a day. And because you're doing because it's an EPC contract, because you're saying to somebody, here's one contract to build this plant, exactly as you built the plant in the reference plant, then you can have delay and performance penalties. If you're going for an EPCM contract, like you had with Medupi and Cassini, where there were like 40 contracts, okay, let's say 4 or 5 major contracts, then you are, as a buyer, you're taking the risk of the interface between those different components. So trying to get any one of them to say we will take liability for being late wasn't possible, because the boiler man at Medupi will say, well, the problem's the turbine, not mine. Or the turbine guy, the problem is the auxiliary plant man. And all those contracts go through Cuba. So you can put in very simplistic time and performance contracts, which is exactly why they're busy with 2 lawsuits, both for enormous amounts of money in Olkiluoto contract. But I would argue that if you look at the other contracts in the world, the Bangladesh, the Belarusians, the Turkish now, and so on and so on and so on, they're all going sensibly on time and budget. Clearly, there was an issue with COVID closing down, had a knock-on effect on big projects. But in terms of nuclear projects, no. Big nuclear projects, if somebody's run a number of them and knows how to do it, like the Koreans, the Chinese, the Russians, timing is really good. What is interesting is if I go back to, just let's go back a second here. I'll show you the interesting, if I may just go back to this one. There is one funny on this graph here I was going to show quickly.
Do you want me to make you presenter there quickly, David?
Oh, sorry, if you can, yes. Can you make presenter again? Sorry, I didn't.
Yeah, of course.
Unpresented. Can you make presenter again? Okay, where's my present show? Okay, sorry, I'm just gonna. I'm sorry, let's go through it quickly, but here. If you look carefully here, these are. What's interesting is you can look at Tianwen 1 and Tianwen 2, and they're over schedule, and they were the first two. They were the first 2 export machines the Russians built after they restarted their industry. I mean, they're in China, and you can see they were delayed because the Chinese had not. The Russians had not done an export deal before overseas, and they learned a lot. And so then you come down here, Kalinin. So the answer to the question is that yes, you will always see first of a class will end up giving you a challenge, and first of a design in a country will give you a challenge. Hence that Pakistan deal I mentioned, where the price between 1 and 2, 3 came down dramatically. If that makes sense.
Thank you, David. Let me just get the screen back to myself now. We have our last, no problem. Our last question we have, and ladies and gentlemen, just while I'm getting this last question, if you want to receive a copy of David's presentation, please drop me an email, minx, M-I-N-X, @saiee.org.za, and I will send you a PDF of his presentation. Okay, our last question today is from Emmanuel Montwedi. He's saying, your presentation clearly shows that if South Africa is to choose a vendor, that should rather be from the east and not the west, due to construction timelines, etc. How do you deal with the diplomatic fallout that may follow, since most of our trade relations are with the west? Do you think this could be a showstopper more than cost of nuclear themselves?
Politics. My answer is that our biggest trade partner is China. I think as long as you make it, there are 5. Let me just say that I've been involved in this process from the ESCOM side over the years in terms of, and there are always 5 key objectives or criteria for selecting a vendor. And note, the vendor was more important than the design. And those were, number 1, have you built a machine of a similar size and scope reasonably on budget and time in the last 10 years? Because if we haven't, then we don't want to be to it. Secondly, have you got a reference machine? In other words, a machine you're currently building or have just finished, which is the design we're going to have. Don't bring me a pile of paperwork. And that also, thirdly is, have you got a domestic program of these reactors that you are building, so that we can have some support? We don't need any guys in the world building this plant. Next, have you done an export job successfully recent at all? In other words, if you're purely working in your domestic market and nowhere else, I worry about you'll learn lessons from dealing with foreigners. And lastly, do you control all the intellectual property of the design you're selling us? Be if you've got to get good relationships with the IP support, and you've got to be staying friends with your vendor for a long time. This is a 100-year project. But if there's other parties involved, then you've got to keep more partners happy, and that's the problem. So with those 5 criteria, totally, then you end up self-evidently coming up with who you think is a credible builder. But my answer is, if you ask who is exporting machines in the world today, as of this moment, it is Russia and China, and to a lesser extent, just finished off South Korea. So, do you buy a motor car from Toyota or not? And politics, I think, if you're absolutely clear, then that should be handleable. But we're in BRICS, so what's the problem?
Thank you very much, David. And that will bring us to the end of our presentation today. Ladies and gentlemen, before we go, I'd like to just inform you of the handouts in the handout section. It is the SAIEE Training Academy brochure. For your information, you can download a PDF format, and the July issue of What Now magazine. Please download it now. I'm going to activate